Hi, my name is Jack West, and today I'm going to be presenting Moonshine, an online randomness distiller for zero-involvement authentication. Today I'm going to be presenting on behalf of my colleagues, Kyuhyun Lee, Suman Banerjee, Younghoon Kim, George K. Theravothical, and Neil Klingon-Smith. The first thing we're going to be discussing is what is zero-involvement authentication. Zero-involvement authentication is a minimal communication security scheme that relies heavily on a shared local entropy source. Meaning, to authenticate onto a network or establish communication with a device using that ZIA scheme, you need to know the entropy source, you need to synchronize with said device with the entropy source, and you need to have the same bit generation algorithm that was used to create the key. All three of these add a layer of security that other security schemes don't offer. ZIA has a lot of potential for the IoT sphere because of the fact it's so scalable and so localized. A lot of IoT systems depend on local environment variables for data gathering or examination. So using those variables to create keys that are local to said environment seems like a no-brainer. So now that we understand what a ZIA scheme is in concept, let's talk about actual projects that utilize the ZIA idea. Volkey is one of those projects here at Loyola. How Volkey works is you plug in two IoT devices in your home, and they examine the wall noise and generate a key based on the wall noise. The idea is the wall noise in your home is specific to you and the devices you are using in your home. So an adversary trying to get onto your home network has to know the exact layout of all the electronics in your house and position them the same way and use them at the same times to hope to generate a key that's even close. So Volkey intends to provide high security based on your home's electronics. Other entropy sources that try to do the same thing are electrocardiograms, shaking two devices simultaneously near each other, receive signal strength, and ambient audio. All of these try to accomplish the same goal: highly contextual, hard to replicate sources of entropy to generate their keys and verify with one another. The problem that all of these examples have, though, is their key quality. So now that we have a good understanding of ZIA schemes and the problems that come with a ZIA scheme, now let's just talk about what makes a good key. And for that, let's just have an arbitrary 128-bit key generator. And you expect the output to be 2 to the 128 possible combinations that are equally likely. When you work with a ZIA scheme, the reality is actually this. You will have all zeros or all ones because you had a very big context event that you couldn't control. Pseudo-random number generators do not have this problem. You have full control over any pseudo-random number generator. But with a ZIA scheme, where you rely on entropy from an outside source that is not in your control, you are at the mercy of the entropy source. Meaning that you generate, if there's an event that creates a skew in your algorithm, you have to live with it. An adversary who's trying to break onto your system, if they know that that occurs, they can just wait for these event streaks to happen and then try some highly probable keys and then more than likely get on. A solution to this is using MD5 hashes. So you cover up the zeros and ones using an MD5 hash and then using that as your key, rather than using the actual number generated from the key generator. The issue is the adversary, all they have to know is that that's what's happening and then change their penetration strategy and still find a way in. It doesn't directly solve the problem of all zeros and all ones. Now that we have a good understanding of the issue that plagues a lot of ZIA schemes, this table represents the relationship between randomness and the said ZIA scheme. What we can gauge from this table is that the randomness is more of a problem of the key generation. To have good keys, you need to have good randomness. And from all the recently published works we have in this table, none of them have yet to pass all 15 NIST tests, which are a very good way to evaluate randomness. Therefore, ZIA has a randomness problem. So now that we've discussed all the issues around ZIA, let's talk about Moonshine's goal as a whole. First thing we want to do is improve randomness for low entropy sources, which would then lead to better keys. Therefore, the requirements for this goal to be met are three criteria: uniformity, scalability, and consistency. Uniformity refers to evenly distributed keys. Scalability refers to a small bit stream is as random as a larger bit stream. And consistency refers to the first bit stream that we looked at is as random as the last bit stream that we looked at. Now that we understand the goals that Moonshine is trying to complete, let's take a look at a statistical property that we found that allows us to meet said goal. And this is the asymptotic equipartition property. To give a rough overview of it, a consequence of the asymptotic equipartition property is the typical set, which is a set within a probabilistic space where the events are equally probable to one another, i.e. if there's two events, they both have the same probability, and when we focus on them, they're equally probable and therefore fully uniform. Heads, tails, and tails, heads for a weighted coin when you flip it twice is a great example of this. Moonshine's novelty is dynamically finding the typical set and designing the new output to be related to the typical set. And we also forward this thought by discarding bits during the warm-up period such that we can lessen the impacts of events that could skew the overall data. Now that we understand the concept of AEP, we can approach ZIA datasets, specifically Volkey, and look at it with a different eye. So what we see here is a histogram of all possible 8-bit binary numbers Volkey produces over the course of 24 hours during one of our experiments. And just by looking at it, you can tell that there is a very large skew versus the typical set versus the non-typical set. There are many more values in the non-typical set than there are in the typical set. So what happens when we apply Moonshine? Well, the set becomes a lot more uniform. We see that going from B to A is a large leap in uniformity, and also we throw out a lot of values. And for reference, Python's random number generator is graph C, and Python's random number generator passes all the NIST tests and is almost completely uniform. And A and C are much closer relative to one another than B and C are. Therefore, Moonshine makes Volkey's data more uniform after being applied. Now that we've seen an example of Moonshine, we can now talk about the details in greater depth. What we see here is an overview and a flow diagram of Moonshine's algorithm. The first thing it does, and then it'll do this constantly, is collect and discard bits. We call this the warm-up period. You want this to be as long as possible such that your entropy calculations and your discarding is more accurate and more attuned to your data set rather than being in short bursts. Upon a key request, i.e. one device needs to get a key from a bit stream, it'll calculate the entropy, discard the non-typical set, remap and compress remaining sequences, and then output an altered, more random bit stream for key creation. So now that we've talked about an overview, let's actually use a concrete example and use an arbitrary binary sequence for that concrete example. So the first thing we want to do is decide what our parameters are. This is sequence length and discard length. That's what Moonshine needs to begin. Sequence length is how many bits you want to have per block, and discard is how many bits you want to discard after a block has been determined. But we'll get to the discard in a little bit. So first let's talk about the sequence length. Like I said, it's just a block size. So you count 4 and you assign a value to it. That's what we do here. Next is the discard. After you count 4, you throw out 4. Count 4, throw out 4. The discard, like we talked about earlier, is meant to minimize event skewing, minimize unpredictability, and also minimize the impact of an unforeseen event that the algorithm couldn't account for. And as we'll show in our results, the discarding bits really helps manage that and maintain randomness. After we do our warm-up period and we're now queried for a key, we then discard the non-typical set. From the last slide, we know that 0 comes up twice and E comes up twice. So for the purposes of our example, we're going to assume that 0 and E are a part of the non-typical set. We then throw out 0 and E only in every occurrence of that. The remaining bits are then compressed down into what's left. This is the application of the AEP that we discussed earlier. So the final phase of Moonshine is the remapping phase. What we do here is because we throw out half of the data set, Moonshine can now remap bit sequence lengths of size 4 down to size 3 because we threw out half of the possible sequences. What this does is two things. First, there's no holes in our uniformity when looking at the new bit sequence. And also, what it does is we increase security, because depending on how you remap the bits, the adversary shouldn't be able to tell how you went from 4 to 3. So now that we've discussed Moonshine's algorithm, let's talk about its evaluation. So our first set of graphs are a comparison between Moonshine and von Neumann for both data retention and NIST test pass rate. All of the data was collected on a Volkey running in real time on the IoT device, and we just swapped out Moonshine and von Neumann. What we saw was data retention past the 2-bit mark was much better than von Neumann's. This is because when you have more bit sequences at your disposal that are possible, the non-typical set spreads out more as well as the typical set, meaning that when you throw out the highest half, you get less of the typical set and more of the non-typical set when you discard it. So therefore, the data retention with Moonshine was much better. Von Neumann, the NIST test pass rate, which is the second graph, we saw that as we increase the bit sequence length, we saw a general trend of better randomness. Because remember, the NIST tests evaluate randomness at in an arbitrary way. There's not a single attribute NIST focuses on all of them. So if we have a better pass rate overall, that means our randomness was better overall. And finally, the last graph focuses on Moonshine speed. Because to be in a proper IoT environment, it has to be fast enough to not hinder any other component of the IoT device. And as we see, if we increase the bit sequence length, it has a linear relationship rather than an exponential one, which means that it's completely usable in a real IoT environment. So now let's move on to the next set of graphs. So let's first discuss what they are and how to read them. These are heat maps, meaning that their color tells us the value. And the y-axis is bit discarded, and the x-axis are bit sequence length, and the color corresponds to the NIST test pass rate. The brighter the color means the more tests they pass. The darker the color means the less tests they pass. These graphs show two important correlations for Moonshine. The first is that if you don't know where to start, a high bit discard and a high bit sequence length will most likely give you good results. I say most likely because car and mobile don't, and we'll get to that later. And the other important relationship that these graphs represent is the arbitrary nature at which Moonshine can take any bit stream and work with it. RF frequency, audio, and Volkey are based on a single source of entropy, whereas car, mobile, and office are based on multiple in different locations at different times. So Moonshine is able to take all of them and show some increase in randomness from their beginning portions. Both of those findings are very important. Now, car and mobile are different because car and mobile had such low entropy that once we threw out a lot of bits in general, Moonshine could not use the remaining to create a good entropy source for the NIST test to evaluate, and NIST test is returned to failure. So car and mobile are purple in the upper right-hand corner because they started with such low entropy that when we got to the higher values of discarding and remapping, they weren't able to keep up, and NIST also couldn't keep up with them. This final set of graphs describe one thing, and that's the difference between the data sets and how Moonshine approaches the differences. But first, let's describe the graphs. Once again, the x and y axis are bit sequence length and bits discarded respectively, and then the colors reflect how much data is retained. So the brighter the color, the more data that's retained. 50% of data is the absolute best case we can have because 50% is a completely uniform set. So if we throw out half of a completely uniform set, we retain 50%. So now, let's talk more about the findings here, and that's RF frequencies, audio, and Volkey all start with the highest initial entropy, meaning that Moonshine was able to save more data because of that initial entropy that it had, whereas car, mobile, and office all had initially low entropies. So when we apply Moonshine to it, to get it to a point where it was random, Moonshine had to throw out a lot more data. So for some general advice for those of you wishing to work with ZS schemes, we offer 3 pieces of advice. First, filter out as much periodic noise as possible, pick a high entropy noise source, and use a randomness corrector such as Moonshine or fuzzy corrector if the bit streams don't perfectly match. And then for conclusions of this presentation, the first is further applications of the AEP does lead to better randomness. The second is Moonshine offers a configurable randomness distiller for any noise source. And the third is ZS schemes do improve when using Moonshine. Once again, my name is Jack West, and I'm here presenting Moonshine, an online randomness distiller. Thank you very much for listening. For further questions or inquiries, my email is on the screen, and if you're curious about my research and other opportunities or other interests I have, my website is also on the screen. Thank you very much.